Can you prove that? Because yeah, exactly. So if V1 then and this is a proper and invariant subspace, right? Right? So if this were irreducible, if this were reducible, tensor this with sign, further tensor with sign, you would get standard. So this calculation shows you that standard tensor sign again gets you back to standard. If this were reducible, therefore so would this be. But that cannot be, because standard is irreducible.
So can we, if B tensor W is reducible, then can we say anything about V?
No. No, not at all. Because most often, no, for example, I mean this is very rarely will V tensor W be also irreducible. This is the case when you take an irreducible thing and tensor with another irreducible thing, you get another irreducible thing. But it's very rare that this is a very loose statement that I'm making, but it is, keep this in mind. It's very rare that tensor product of irreducibles, it's rare. It will now almost never happens in
standard tensor, standard is.
Of course, there are, what I'm saying is that is count. If you tensor with a one-dimensional thing, yes. Yes, because of every one-dimensional thing has something when you tensor it with such that.
How do we assign because of?
That's not very difficult. If G to GL1C is a representation, just take, so let's call this rho. Define rho inverse to be G to GL1C, rho of G inverse on G is G rho G inverse. That's a representation. Because composing this, that's like composing, this is the inverse. This is okay. This is a group homomorphism because it's an abelian group. G going to G inverse is not a homomorphism for groups. It's an anti-homomorphism. But for abelian groups, it's a homomorphism. So GL1C being abelian, that's an abelian. That's a homomorphism. So composing this, you get rho inverse, and you can see that rho inverse tensor rho is trivial because this is one-dimensional, this is one-dimensional. It is, the generator is E tensor F, if the E is the generator here and F is the generator here. On E tensor F, how does an element of G act? It acts as rho G here, by the scalar rho G here, by the inverse of that scalar rho G there. So by 1. So if you tensor with a one-dimensional representation, the irreducibility will not change. If it was irreducible to begin with, it will stay irreducible. If it was not irreducible to begin with, it will not be irreducible, period. So when you tensor with an one-dimensional representation, the irreducibility is maintained, or lack of it is maintained, yeah.
But again, you will cross with
Mm. You can go back. That's a reversible action.
Something else, your sign inverse is itself.
Yes, that's what we were using here. Right? All right, so, but rarely, or I think one can say never does. I mean, there are situations where that is true when tensor products of irreducibles are irreducible, but not for, it's a rare occurrence. I mean, if you, some of you were in Ravinder's talk, student seminar. So there he had examples of where you took two irreducible representations and then you got something irreducible. Okay, but that is, just keep this in mind. It doesn't ordinarily happen. Yeah, for the moment, just remember that I said this. It's a rare occurrence that tensor products of irreducibles is irreducible. Of course, not with one-dimensional one.
If I have given one character, I can find a representation corresponding to it.
Given a character, what do you mean by character?
Character is just a line from G to split.
Such that
So it is a conjugation.
that's called a class function, not a character. Okay, a character is by definition the character of a representation. Okay, so is every class function a character? No, because you can take half a character, half an irreducible character. See, what are class functions after what we have said? The class functions are the C span of irreducible characters, whereas characters are the N span of irreducible characters. Right? How do you get a character? It must be a sum of irreducible characters. No? It's a non-negative integral linear combination of irreducible characters, whereas a class function is a C linear combination of irreducible characters. Okay, so it looks like if you think of the irreducible characters as spanning a vector space, they are orthogonal also. So with respect to that inner product, you can think of them as being like this. Then I mean, of course, when we think of pictures, we always think of real linear combinations, not complex linear combinations. But with that caveat, say if you have three irreducible, S3 has three irreducible characters, you can think of as three-dimensional space. The vector space is of course the whole thing. But what are the characters in this? They are the non-negative integers. So it's like this octant, the integral points in this octant that you have. Non-negative integral linear combinations of these 3 points. So the first octant, whatever it is called. Okay, that would be the not quite. It's not quite a lattice because this half is not there. Lattice generally means that it is an abelian subgroup. It's a subgroup. It's a subgroup. Okay, So, yeah, I know in what sense you are using the term. You are using it in layman's sense. It looks like a lattice, right? But lattice, just be careful because normally lattice, when they say in mathematics, it's a subgroup. Here it is not a subgroup because the negative of a character, of an irreducible character.
So what is it that is part of integer? And the first octet, the linear combinations are
Only the integer points.
the integer.
Like if you had two irreducible, for example, for the group Z mod 2Z, there is sine and I mean, there is trivial and sign. So there the you could think of this whole space as the space of class functions, whereas the characters would be the integral points in the first quadrant. Non-negative linear combination of irreducible characters. Okay, it's a very important distinction. Yeah. So if you think, see, you can think. So what Amit was asking was, how do you? I mean, we have said that the irreducible characters form an orthonormal basis for class functions. So, but the word character should not be confused with class function. Class function just means, as he said, it's a scalar valued function which is constant on conjugacy classes. That's what a class function is. Of course, all characters are class functions, but they are special types of class functions. Okay? For example, if you think of, so the space of all class functions is a vector space, is a complex vector space. I mean, here I'm thinking, I mean, I'm drawing the real picture of that, in which has as much dimension as the number of conjugacy classes, right? So, and it has an inner product which we have used, and the characters, irreducible characters, form an orthonormal basis with respect to this inner product. So you can think of that as if you have, you can, the usual picture if you have of Rn or Cn, right? Rn, Cn, but actually only Rn in your imagination. I mean, when you think of it as a picture, at least in mind. Okay, so that you can think of it like that, and if you do, then the space of all characters is every point in that vector space, every point in that space. Whereas the characters would only be the non-negative integral linear combinations of the irreducible characters. So in this case, for example, if we are thinking of S2, it's a group with just two conjugacy classes, right? So therefore, the space of class functions is two-dimensional. So you can, this is the trivial character, this is the sign character, and any character is only an integral linear combination of this. It's some 5 times this and 7 times this. It's a non-negative integral linear combination of these. So it's the integral points in the quadrant, whereas class function is any point on this vector space. Okay, this is a very important distinction.
Because they are the C-linear combination of
Exactly. So it's a question of C linear combination or N linear combination. Is this clear? Okay, that's all. So be careful in character and class function. They are distinct, right? Okay. Any more questions?
In the book, they have not explained how they just said like for this monster group they calculated all they gave the character table. So when we don't know the structure of the group properly, how do we, are there techniques, standard techniques do we follow?
Okay, this is beyond the scope of this course for sure, and also beyond the scope of my competence. Okay, so no, see, it looks mysterious, but if you start looking at it, the mystery sort of unravels itself. So it's not. It doesn't sound so. Maybe I've heard it so often that it doesn't sound so mysterious to me anymore. Okay, but sorry. I mean, I definitely, there's nothing intelligent I can say standing up without preparation. So that question will have to be shelved. Maybe you can Years later, you can tell me about it. Okay, so should we just, so there are two more things which I wanted to do before coming back to the examples. Namely, we were discussing about isotypical components, and there were two things that we wanted to do, task 1 and task 2 of the last lecture, right? Task 1 was show that the isotypical components are unique. I mean, of course, this is sort of putting the cart before the horse. To talk of isotypical components, you had to prove the uniqueness theorem, so that's what I mean. So there was a uniqueness, and we said, so we did that, so I will not repeat it for, we've already done task 1, namely to show that so our context is G is a finite group, base field is C, and V1, V2, Vn are a complete list of irreducible representations. No two pairwise distinct. Okay, I have not said it, but then the statement was, you let V be any okay, so V be any representation of G, finite dimensional representation of G. Then write V is equal to U sub 1, U sub 2, etc. with Ui irreducible. Right? You can do this by Maschke. Right? It is completely reduced. It is completely reducible. So now define U upper j to be sum of all those U sub k such that U sub k is isomorphic to V sub j, where V sub j is this particular irreducible representation. Okay, so claim was this was task 1, which we finished. Show Uj is independent of the choice of the decomposition. So you could have, see, we all agree that this decomposition could proceed in many different ways, right? You could choose one irreducible subspace, choose a G complement, and then somebody else comes along, choose another subspace, another G complement, and the paths you take could completely be very different. However, so while this can be very different, after you do this for, in your way and compute U upper j, I do this in my way and compute my U upper j, say U prime upper j, while U prime lower j and U prime j, I mean the U primes need not have any relation with the lowers. U prime uppers, U upper j will be equal U prime upper j. Okay. In fact, the way we proved this was, in fact, Uj was the image of the natural morphism Vj tensor Hom V to Vj or Vj to V to V.
Oh,
Okay, is something missing here?
you will need element and you have to apply to G of G. Yeah,
Vj to V. Is something missing in this?
G.
No, this is G. So that was a simple observation. So look back at the video of the previous lecture for a proof. Okay, if you, so I will assume that we know that and proceed. Okay, now task 2 is now, so notice, okay, that hom G UK UJ is equal to 0 for k not equal to j. Why? U upper j is a sum of copies of V lower j. U upper k is a sum of copies of V lower k. But there can be no map from V lower k to V up lower j unless k equals j. I mean, no non-zero map because they are irreducible and pairwise non-isomorphic. Okay, so there is a unique G projection from V to any uj. Okay, why does, what is the reason for this so, right? Okay, here V is equal to U1, U2, U3, etc. Okay. If this j say, let's say it's 1, okay, why is there a unique projection from V to U1? On U1 what is it? It must be the identity. On U2 what is it? It must be 0. U3 it must be 0. UN it must be 0. So it is bound to be, so it is determined everywhere on V. Therefore it is there is a unique projection. Right? Yes. So there is a unique projection from V to uj. So find a formula for it.
But we have to equal to direct sum of uses.
Yes.
Move upper J.
Yes. That is
From there.
that sort of, we have not proved it, said it, but that's obvious because you're just yes, rearranging and then summing.
Then of course, because that was the complement of you will get.
Yeah. So there is no so if I have something equal to A direct sum, B direct sum, C, then if I take A plus B and then C separately, it's still the direct sum of the sum of A plus B and C, and so on. So that part is easy. I have not.
And if U's are G space, like you are taking G representation, right? So you get the G projection.
Why is it a G projection? Well, on C.
But they are the G complement, right? Except U.
So there is a G projection. Namely, send you take identity on that U1 and the 0 on the rest. Right? That is a G projection because it's a sum of G maps. Okay, so this is a nice, so let's go ahead and do this, use this formula, do this formula. It might seem like I am pulling this out of a hat, in the sense that there is a, you do something very nice, some trick, and you get the answer, and it's a beautiful answer. So the thing is, the trick is very useful. It is like, if you wish, construction in geometry, right? You're given some problem and you have to make some construction, right? And that construction isn't obvious, but if you draw that, somebody comes along and draws one straight line somewhere, joining some 2 points, and lo and behold, the proof is transparent, right? You can see the proof. Similarly here, again, this construction is very standard. It's a standard trick. So you should sort of know this trick, right? So how do I expect to find a projection? So, well, so here is a, I will just do it, and you observe that it is, that it works, and then you add this to your kit of tricks. You add this to your repertoire of, you understand what I'm saying? Repertoire meaning the things you are comfortable with, your toolkit. You add this to your toolkit. Okay. Okay. So here is the idea.
If suppose that you want to add some into that initially you have written, and that how many as of copies with the items you have written. But again, without doing that, one can get G projection also to U1.
U lower one, yes.
U lower one can get also G projection from V to
V lower one, yes. U lower one, yes. But you can get a G projection, but it doesn't even make sense to ask if this is unique, because your U lower one maybe very different from my U prime 1, U prime lower 1. This question makes sense only because this Uj is independent, right? So this would, this would make. Yeah, there is, of course, you can always talk about this. There is, once you have a decomposition like this, there is a G projection where you send this to itself and the rest to 0. Absolutely. There is no problem with the existence of that G projection, but doesn't, okay, so what? Yeah, but here it means there is a G projection and this Uj is unique, right? So the G projection is also unique. So for what is the formula for it? How do you find it? Okay.
Like the same thing again, like we take a number as prime factorization. We are taking all the prime powers, like 2 to the power 3.
In a sense, yeah. Yeah. Yeah, there is some analogy, yes. Yeah. It's not clear how far that will carry, but there is some analogy, yes. Okay. Okay. So how do you expect to write? So projection, I think of it as a map from V to V. It's a map from V to E, which is identity on Uj and 0 on the other upper V upper J's, right? How do I think of, I have to write an element of end of V. I have to write an element of end of V. How do I write that element? See, okay. So thinking ahead a little bit.
The basis of the end of V will be given by the basis of V and this thing.
Very good. So you can, if you know a basis for V, then you know a basis for end of V by, there is a standard way to get a basis for end of V from basis for V. Okay, very good. Because end of V is V star tensor V. You take the basis for V, take the dual basis for V star, and then V star tensor V is isomorphic to NV, V is finite dimensional therefore, and therefore you get a basis, natural basis Phi star, EI star tensor EJ for NV, right? Correct? Okay. No, that's not how. See, correct. No problem with that. That's not going. That's not of very much help in this situation. What is? See, we want to write elements of G. See, each element of G is a matrix. So I try to write it as a linear combination of elements of G. Okay, so consider chi G GV, so G sub V, by that I mean the corresponding linear transformation on G. Right? This is an element of NV, right? So where chi is any function.
Not necessarily a class function.
Okay, I will come to that. I am going to make this into a class function. If I make it into a class function, then what can you say about this element of NV? No, I have not taken irreducible representation.
But there is some of lambda is
No. But before that, don't jump. You can say something. Suppose this is a class function. V is not irreducible.
center.
This belongs to the center of. That belongs as an element. So it belongs to the center of the group. In other words, it commutes with all elements of G. So this belongs to end GB. Right? This belongs to end GV. So if V phi is a class function, okay? So my attempt therefore is to try and compute. Okay, so see, this is a G projection, therefore it is I want an element of end GV, right? So it is natural to try to take a class function here and GV, right? Okay. So if chi is a class function, then this thing it commutes with all elements of G, right? Right, okay.
Keep it on.
So now assume chi is a class function. So this is an element of NGV, right? So let's give this a name. Let's give this, what do you want to give this? I want to call this chi tilde. Chi is a function, so chi tilde is its corresponding so chi tilde leaves every G invariant subspace of so what do I want to say? Let's see. Okay. Now another thing that is obvious is chi tilde is okay. Let's compute chi tilde restricted to V sub j or U sub let me cite L for some L. Okay, what do we mean by that? So this goes from U sub L, which is a copy of some irreducible representation. Okay, what is chi tilde? It is this. Okay, G UL is an G invariant space. So if I act this on an element of UL, GV keeps that in UL, and this is a scalar. So you will get a map from UL to UL, right? But then by Schur, more than that. We are over complex numbers. So this is UL is G invariant, and then yeah, it is. So by Schur, this is multiplication. This is a homothety. This is a scalar multiplication. It's a scalar multiplication. Okay. Now we apply our usual. Now I want to compute that scalar. Okay. How do you compute that scalar? Well, here I compute the trace of this. So to compute the scalar, I compute the trace of this. So to compute this scalar, compute the trace of this map, trace of chi tilde restricted to U, and divide by, what should I divide by? Dimension of UL. Correct? You have a scalar matrix. To compute what the scalar is, you compute the trace of that matrix and divide by the dimension of the. It seems like a contrived thing to do, but that's what works. Okay. Okay. So let's take trace of that. So trace of chi tilde restricted to UL is equal to trace of chi g GUL is equal to, I can is equal to trace of, so chi g trace of GUL. This is okay. I have written GV here, but then I have changed it to GUL. I hope that is okay. Right? It is just, yeah, restriction, exactly. So this is equal to chi G chi UL. Okay, chi, let me say chi L of V, chi L of G, if, okay, or let me say here K, where U lower L is isomorphic to V sub K. Right? I have fixed some UL, some arbitrary UL. It's isomorphic to some V sub K, and I've computed the trace is equal to this much. Okay? Okay. Now what do I want from it? I want that this scalar, I want it to be 0. See, so again, like I said, I'm pulling this out of a hat, but I'm trying to make the procedure very reasonable, and the procedure is, it's a beaten track. You keep following this track, you know, it leads you to lots of things. Okay, so, and the beaten track is like this. I mean, so what do you want? What do you? I wanted to compute my. See, how did we start? We wanted to compute the projection. So I took advantage, I took a class function and tried to write this class function, and I'm trying to compute chi. Yes, I'm trying to compute chi. What do I want of chi? Let us think about what do I want from chi. I want it to be the projection to U upper j. So, or let's say U upper k, U upper k. So what do I want? Sorry, say U upper j, U upper j. So what do I want? I want that when this k equals this, I've now taken this L and computed it. If this k equals j, I want this to give me, I want the scalar to be 1. Right? I want the scalar to be 1. If, on the other hand, if it is not, then I want it to be 0. Now, you know something about these, you know something about orthonormality of the characters. So, can you guess what chi must be? See, I want this to be 0 for something. Chi j, if I put chi is equal to chi j, will it work? Okay, no, forget the division, that we will adjust at the end. If I don't get 1, I get some other constants, that we will adjust. Okay, don't worry about the chi j bar. Chi j bar will work. Okay, observe, if we put chi equals chi j bar, okay, then this here is 0, okay, let's compute it now, is 0 if k not equal to j, right, and what is it otherwise? No, cardinality of G if k equals j. Right? So it seems to do what I want, except that I have to appropriately normalize it. Right? So what do I have? I wanted this to be when on copies that are isomorphic to Vj, it must be identity. On copies that are not isomorphic to Vj, it must be 0. Right? So this part I have achieved, and I want to make this. So let's see. I want so, but this so. In order that chi tilde restricted to UL be equal to identity, right? Okay. Identity if UL is isomorphic to Vj, 0 otherwise. Okay? Okay, we must take chi is equal to chi sub j bar. Okay? If I take chi sub j bar, I will achieve this. But will I get identity? That's the question. Okay, let's see what I need to do. Okay. So this is the trace. Okay. The scalar is this divided by the dimension of UL or the dimension of Vk. So right. So I do a. So you can fix this by just working this out. Okay. So the trace, I want the scalar to be 1, right? But what is the scalar? The scalar is this. So I put chi j bar now, right? It's clear that I should put chi j bar there. Okay. And then 1 over. I should put dime UL. UL is k. So if I put, let me just try that. Right? If I do that, not quite. Oh, not quite. I want the so. If I put dimension of Vj up and divide by G, I claim that will do the job. Right? Because if I use this to be my, so finally the answer is, but my chi must be this. This is my function. Right? If I do this and do the computation, okay, let's see. If I do this, then I substitute this here, right? And compute. And then what do I get? I get dimension of Vj, which if I divide by dimension of Vj, I do get 1 for the trace. Okay? So finally take, this is a matter of adjustment. Okay? Just a matter of adjustment. Take chi is equal to dimension of Vj chi j bar divided by cardinality. So the final answer is, it's sometimes called in Fulton-Harris, for example, it is called the second projection formula. So I don't know how standard that is, but the first projection formula is the 2Vg, that is the V upper G. It's the special case of the it's the special case of the second projection formula when for the trivial representation, the trivial isotopic component. not just one dimensional, they are trivial isotopic component.
And the direct sum of the trivial.
Yes, in other words, V upper G, all those fixed points of G, fixed points of V. Is second is it says this is projection to the isotypical component of V with respect to irrep Vj is given by sigma, there we have dimension of Vj, this is the dimension of the irrep divided by the order of the group, sum over G, I should take chi j bar G G V. That's this is the formula.
That one was like summation. Averaging, we have done that is also one kind of.
Okay, if you, so what is the averaging?
Just dimension period one.
Not just dimension meter.
Just characters are what?
Character. No, say that again.
Irreducible representation. No, because that will be only chi j of G bar is 1 V. Because there is a written defined G 1 by R.
Yeah, so if you put trivial here, this becomes 1. So this becomes 1 over a cardinality of G, sigma G, because this is always 1. But that is the projection to the fixed points, the trivial isometric component. Yeah, but it's a good question. When you have a second projection formula, you should ask what the first one is. The first one is the special case when Vj is identity, trivial. Averaging, yes, that we have already seen. Okay, so this formally finishes the, so I've, as you can see, the ideas are repeated, right? There is Schur's lemma, there is averaging, there is, you use, the standard thing to think about is you take a function and take some, you write sigma chi g g and think of it as an element of the group ring, think of it as an operator, right? That's one technique that we have learned. And then we've observed that when chi is a class function, this element of the group ring commutes with all elements of, is in the center. Therefore, if as an operator on a G space, it commutes with all elements of G, right? Okay. Therefore, by Schur's lemma, if you have an irreducible representation, this must be a scalar, right? And to compute that scalar, what you can do is, if you are in characteristic 0, to compute that scalar, you can compute the trace of that and divide by the dimension. Okay, so these are the basic ideas. You keep using them in different combinations, you get all the proofs. Okay? Okay. Now, let's come to some examples. S5 and Dn, right? This is what Sumit wanted. Done. Okay? Okay, I should give myself enough room. How many conjugacy classes does this have? As many as partitions, right? So I'll just write 1 here and 1, right? 1, 2. I just write 1. What's the number there? Hmm.
5C2 cross SW2 by 2.
Ah. So what is that?
5C2 means how many?
10.
Five into four into three by five P three by three.
So tell me the number.
Huh?
Tell me the answer.
20.
20. What else should I write? I'm getting a different number. Okay, but let me not write sign here. Let me write standard here. Okay. I'll also write some symbols here. This is just so cycle classes are like partitions of 5, right? Partitions, you can think of them as pictures like this. These are called Young diagrams, right? How many partitions of 5 are there? So I should give myself enough room, which I have not done. Okay, this one I need at least. Okay, let me see if I have enough room now. Okay, no, I have. Right, and then there is a 2, 2, 1, and there is a 2, 1, 1, 1, and then there is all 1, 1, 1, 1. Okay, I am pulling again something out of the, for Sn, this is always, you see, of course, here they are all, these symbols correspond to things here. For example, this corresponds to everything being 1, 1, 1. Here being it is 2, 1, 1, 1, which is corresponding to this. This could be 2, 2, 1, which is this. This could be 3, 1, 1, which is this. This is 3, 2, which we have not written yet. How many, but you have not told me how many elements here. Huh? No, I don't agree. No? No? Okay, first how do you choose those 4 elements? 5. There you leave out 1, 4 elements. 5C4 is 5. After you've chosen one set, how many can you make? How many 1, 2, 3, 4, 1, 3, 2, 4 or 2, 3, 1, 4. You can make 3 out of every 5 choices, so it's 15. See, you pick up a bunch of 4 from 5, that is 5 ways, and once you have picked up that bunch of 4, you can do 1, 2, 3, 4 or 1, 3, 2, 4 or 1, 4, 2, 3, right? So it's 3 times 5, which is 15.
I trusted 5 choose 2 into 3 choose 2.
Okay. Okay, maybe you made some mistake somewhere.
I have to divide by 5.
Hmm. Hmm?
Because 1, 2, 3, 4, 7 as
Okay. How many here? So, let's see. I hope I have enough. So, 2, 2, 1, 2, 1, 1, 1. Okay, 3, 1, 1, 3, 2. And then 4, huh? 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, that is like how many? 1, 2, 3, 4. Okay, that looks okay. Tell me the numbers here, please. How many here?
5, 2, 5, 5 choose 5 is 1 way.
Huh? 4 factorial. Because this one is, you pick all 5 elements, there is no choice. You can always make the first one 1. And once you make the first one 1, there is a unique way you can write it. Right? So it's 4 factorial. How many here? 5C4 is 5. No. 5 into 3 factorial. How many here? No, apply. Yeah.
So 5C3
Yeah, which is 5C2.
into 3C2
What?
into 2C2.
Why 2C2?
Because
Okay.
assembly.
Yeah.
By 2 factorial.
Ah,
By 2 factorial.
into, yes,
And-
2
And
factorial.
by 3 also. Because
No, well, okay. Each of us does it his own way. Okay, what is the final answer?
6.
Well, no, 5C2, it's 5 choose 3 is already 10. 10 into 2, 20.
3 into 2 into 1. 5C3 how much? 5C3.
Okay. So this is the sign representation. Don't ask me at the moment why, but this symbol is for the sign. Okay, there is some association between these symbols and the diagrams and the symbols. Of course, there is a matter of convention whether this is trivial and this is sign, or this is sign and this is trivial. It's a matter of convention whether you want the row to be trivial or the column to be trivial. Okay, there's some. Okay, so but anyway, this is extra bit. You need not worry about this. This is just you can ignore this. Here it is. Tell me the numbers here. Tell me what is it here? How do you compute the standard? 4-dimensional. How do you compute its character?
First is 4.
First it's 4, yeah.
That will be 2. 1, 2 will be 2.
Aha.
So that is going to change 1 to 0. That will be 2. Why is that? Because 4 cross 4 matrix, it is just going 1, 2, 2 and 2 to 1. And 1, 2, 3, 1, 4. And 1, 2, 3, 4, 3, 1, 2, 11. 1, 0. Four dimensions. Total count to 1, 2, 3, 4. अच्छा 1, 2, 3, 4 and 4, 5. That is
नहीं, -1. But ask Avijit how he got it.
how we did explore it.
See, the point is, you're forgetting that, see, you're trying to do something complicated. See, that complicated, it is complicated, but you attach something simple to it and it's become simple. Namely, recall that standard plus trivial is the defining. The defining representation. The defining representation had basis E1, E2, E3, E4, E5. There the character is just literally the number of things it fixes. So this fixes 1, 2, 3, nothing is fixed. And then you have to subtract the trivial, which means I have to subtract 1. So here it fixes 3 elements, I subtract 1. Here it fixes 2 elements, I subtract 1. Here it's 1 element, I subtract 1. 0, I subtract 1. Here 1 element, I subtract 1. And here none, I subtract 1. Minus 1. Okay, now tell me, if I take standard tensor sign, right? Do I get something different from standard or do I get back the standard? From the character table. Very good, very good. Second one will become -2. So it is different. So let's write it here. So when you tensor with standard, what will happen to the shape is it will transpose itself. So what was like this, the row will become column. So what was like this becomes aisa. Okay. So this is 4 minus 2, 1, 0. Tell me please.
1, 0,
Okay. Okay. 3 are left. Okay, what do we do about that?
As you said, 4 one can get always.
Hmm?
For Sn n greater than equal to 4, we will have always 4 representatives.
Yes.
And they are
Yeah.
very easy to write. One can get.
Yeah, one can get these 4, yes. Okay, yes, indeed that's easy to write. So far we have done only easy things, yeah. Let's see if
How many we have to write 120 is equal to this 4 square plus 4 square. 16 plus 16, 32 plus 30. And 120 minus 36. square plus c square is 86.
And observe, so from what I have said, if you believe me, this and this will have the same dimension.
Transpose, they're just a transpose.
Yeah, they have the same, they will have the same dimension. So 2a square plus b square is equal to 86. What are your guesses for a and b?
Four and five.
4.
5 square into 250
Hmm.
plus so that is coming 76.
Hmm.
25 into 250 plus 6.
Can I explain how it
So we are computing these numbers, what they must be. This must be, this is the tensor sign of this. If you believe what I said. This, I'm just pulling something out of the hat. See, you have to, see with this, to try to compute this, you must have some experience, some hard work you need to have. So, this must be the same dimension. So, they call this A, call this B. If I do that, then I have 2a square plus b square must equal 120 minus, this is 17, this is 17, 34. How much is that? 86, huh? Okay, so what thing solves that? Right? Hmm?
It is equal to 5 equal to
Hmm. Okay. Now, this must be, what happens to this tensor with standard? Oh, sorry, tensor with sine. Hmm.
6 times.
No, you will get the same thing. So, what can you say about this, for example? Why? This tensor, whatever number you put here, that into minus 1 is equal to itself. So, what is such a number? 0.
So what is the tensor? Could you repeat what
Yeah.
what this is? How you will
This tensor sine
is
itself. So, this number that I put here, if I multiply that by minus 1, I get back that number. Some number such as that if I multiply that by minus 1, I get back that number. What is that number?
1.
No, 1 if I multiply by minus 1, I get minus 1. 0. So, you can fill this out.
Wherever there is -1,
You have to put 0. There is no choice.
We have to only put 1.
No, no, need not.
X. Anything.
Anything will work. Okay, let's see if there is something else we can do. So, yeah, you could use orthogonality to do it.
That's two variable, two equations.
Hmm? Okay, so you have to know somehow.
The norm is 1 and its product with inner product with trivial is
you could use the inner product with this is 0, you could use the inner product of this with 0, inner product of this with 0, inner product of this with 0. So it will cut down the dimension by 4. So these three things, you know that they live in a 3-dimensional space. Okay, so it gives you lots of conditions, but of course that's working that out isn't a. So the other thing you could do is try and find some standard, some representations that you could, something that it acts on, right? For example, 5 choose 2. So there is S5 acts on this class, right? You could try to figure out how many are. So let's do that example. Let's see how, here is a question. So let's compute S5 acts on the conjugacy class are consisting of transpositions. Okay, linearize this action. See what you get.
When we linearize the defining action on S5, the dimension of that will be smaller than the dimension.
Defining action of, if you linearize the
Defining action of S5.
on 1, 2, 3, 4, 5.
Yeah.
Hmm.
So there the dimension is 5,
Hmm.
but here the dimension will be 10.
Yes.
So I will be doing something more difficult.
Yeah, we are. We have to, because we are trying to find something. We know we've already done that. That has given us trivial plus standard. Okay, so maybe what you're asking is, why not look at the defining representation first of all? I'm saying, yes, we've already done that.
Already done that.
We've already done that. So that has given us this and this. We have to somehow get our hands on some representation here. How are we going to do it? That's the question. Okay, so what you could do is try and take, for example, take the tensor product of this with itself and try to break it up and see what you get. Okay, or let's see what else. Yeah, that's the maybe tensor product of standard with standard. Okay, or this with this, and then break it up and see what you get. That's another way. You just have to try. Let's try this just as an example. Okay. Okay. So what is chi of this? So I will again write here chi, and then I'll write 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. Right? The chi for this particular linear action. Right? So so how many things does this fix? Everything. So this is 10. Anyway, this is the dimension of the representation. This is we are computing the character of this linearized thing. Right? So the basis for this is just transpositions. The character is just the number of elements fixed by acting by that element. So how many transpositions will 1, 2 fix? So 1, 2 x phi 1, 2 is must be equal to x phi. 8. Which ones are those?
3, 4, 5.
Okay, out of 3, 4, 5, anything out of 3, 4, 5 it will fix. And how many there are? No, 5, choose. No, I mean 3 of them. 3, 4, 3, 5, 4, 5, it fixes those. Anything else? It fixes 1, 2. Fixes 1, 2. Right? So how many does it fix? 4. Looks like that, unless I am making a mistake. Right? How many does 1, 2, 3 fix? Which one? No, identity is not a transposition. 4, 5. It does fix 4, 5. It commutes with 4, 5. Not 1, 2, 3, 1, 3, 2. Inverse.
So how is the tie of 1 to 6?
How many transpositions does 1, 2, 3 fix?
4, 5.
Nothing else. I claim. You see that? I hope I am right.
And that is the trace of that is 1.
Trace of the, it fixes 1, so the trace must be 1. See, it's a permutation matrix. The character is,
Sir, it fixes 4 and 5.
it fixes the transposition 4, 5. It's how many transposition it fixes. We are not doing the defining representation. We are doing the one on the number of transpositions. How many does 1, 2, 3, 4 fix?
4, 5.
This okay. How many do I write here?
1, 2, 3, 4. No transposition. 0.
Why doesn't it fix 1, 2? It fixes 1, 2, it fixes 3, 4.
Except 1, 5, and 3, 5.
So what all does it fix? It fixes 1, 2, it fixes 3, 4. It fixes only those two. About 1, 2, 3, 4, 5. Only 4, 5. 1, 2, 3, 4. Okay. Right. So let's see. Can I? There is always the trivial one in there. Right. So do I can check if this occurs in there. Can you check if this occurs in there? Let us check if this one occurs in there. How do you check that? This, I want to decompose this.
So 5 or 6 elements.
No, I don't know.
If this 6 irreducible.
I'm just trying if how this decomposes. Okay. So, for example, if I try it with 1, right, what do I get? How many trivial copies does it have? So this representation, call this V. So this V, linearize this action to get, so this is V. This is chi of V. So I want to write V is equal to something trivial to something plus dot dot dot. I want to write this. What do I write here? So I take the inner product, just follow your nose. Calculate the inner product of this with that. So if I take the inner product, this gives me 10. This gives me 4 into 10, 40. Because I have to multiply by this, right? Right. So there are these columns don't matter, right? 10 plus 40 plus 20. That is how much? 70. 70 plus 100. 120. So it seems like our calculation is right, right? Because I have to get an integer. Divide by 120, I get 1. So this is one copy. Okay. So there is something there, right? Avijit. Please. Okay, just one copy. So so let's see if the second one occurs there. 40 plus 4 into 2 into 10, 80, plus 20, nothing, minus 20. Okay. So that occurs once. Okay. Okay. So that is standard. Okay. Now let us subtract these two from that. I don't know. I don't know. So let's, I mean, I really don't know. Not that I'm acting that I don't know, but I really don't know. So let's try. Okay. So trivial, so let's subtract trivial, subtract standard. Okay. But trivial plus standard I know is defining, which is 5 0 0 0 0 0. Right. I need to subtract these two. Right. So I know that chi v minus chi standard, chi trivial minus chi standard is equal to chi v minus chi defining. Right? What is that? So I just subtract 5. So that this one is equal to, I subtract 5 0 0 0. Oh, sorry. Sorry, not chi defining is, oh, let's just do it. Okay, you're right. So I was, for a minute I confused with the group left regular representation. Yeah, sorry, I made a mistake. Okay. Okay, let's just do defining and just subtract, literally. So 5 here, because this minus how many it fixes in the defining. This minus 2. This minus how many it fixes here.
So here defining is
By defining I mean action on 1 2 3 4 5. Linearized action on 1 2 3 4 5.
so why should
Because I know that it is standard plus trivial. Okay. So here 2 minus what this fixes in the defining. So okay, that looks somewhat promising. Let's can we check? Yes, of course, it's easy to check. So let's check. This is 25. 25 plus 10 plus 20 plus 15 plus 20 plus 30.
Oh,
So how much is that?
40, 60, 70, start the bar.
Got it. Okay. So I don't know whether it is this or this, but anyway, so this is 5, 1, minus 1, 1, 1, minus 1, 0, and so we know what this is. Huh? So this one will be minus 1, this one will be so I copied it. This is a 0. The one before that is no. Is it okay? Okay. Good. Okay, can you fill this in now? Hmm? Very good. Excellent. Excellent. He is suggesting you can find this by just taking regular representation, subtracting 1 times this, 4 times this, and then divide by 6. You got his, you got, no, you didn't understand what he said. Okay. So if I know all but one of the representations, right, then what do I do? You could use that. You could just find this by just knowing that these two are orthonormal after you normalize in something. So you can find this, you can find this, you can find this. Right? You can just write out some, see, this is orthonormal to this. Yes, so if, for example, if I write something here, I take the orthonormality condition here, this will give me something here, and similarly this with this with this. I can do that. But he has another idea. That is, suppose I know all the suppose I know all but one representation. Okay, how do I get it? Well, I just subtract it from the regular left regular representation. See, if I subtract 1 times this character, 4 times this character, because this representation occurs 4 times. It each occurs as many times as its dimension. So I multiply this by 1, multiply this by 4, this by 5, this by 5, this by 4, this by 1, and subtract it from 120, 0, 0, 0, 0, 0. Because that is the character of the left regular representation. The character of the left regular representation is 120 for 1 and 0 for the rest.
But why should that be reducible?
That won't be irreducible, but you divide that by 6 because you know that. See, if I know that, look at this case. I know that there are 1, 2, 3, 4, 5, 6, 7 representations. I know 6 of them. I want the 7th one. I know the cardinality of the group. What do I do? I take each of those that I know, multiply them by their dimensions.
No. Sir is saying any representation you can write as a linear combination of irreducible representation. And we know all. And we also know the regular representation. Unknowns you can find it from the known one. Even that regular representation may not be exactly not irreducible, but we have to find similar ones.
No. But what he is asking is, after you do that, how will you know what you are left with? Right? That you will know because that character will be a square. The square root of that first of 1 will be the dimension of the representation. You divide by that. You get the answer for the 6th one.
But using the orthonormality condition will be easier.
It will be easier in this case, but again you have to do that 3 times.
3 unknowns.
Yeah, here you can do it.
So because that was also making some because we have known the equation to solve that
नहीं एक एक का अलग अलग कीजिए ना. You call this A, just try this orthonormality, that will give you this E. हाँ, column wise कर लीजिए ना. Yeah, little bit, but okay, so you can fill that. Okay, we haven't done the dihedral group, but anyway. So the exam on Wednesday, 10 o'clock. I'll book a room, maybe 1, 2, 3. Okay, this room is there, but maybe 1, 2, 3 is more comfortable. We can be more spaced out.